All right, so this lesson is on the fundamental theorem of calculus. Okay, so the way this is presented, like if you look this up in a textbook or sometimes if you like search it up online, is more complicated than it needs to be oftentimes. So the fundamental theorem of calculus, what happens is like teachers and textbooks try to make it really mathematically rigorous and precise, and then we like lose the fundamental understanding that we're trying to get, right? So I want you to connect this idea of the fundamental theorem of calculus in your head with this phrase in words first. So derivatives and integrals are opposite operations, okay? So again, this isn't the most rigorous way of stating the fundamental theorem of calculus, and it would help if I spelled opposite, right? Opposite operations. This isn't the most rigorous way of stating this theorem, but it's the most important understanding that you need from this theorem at this point in your calculus career. Okay. More formally, here I will show you. More formally, this looks like. Okay, so here's where you have to think a little bit harder, right? So this says that an integral from a to b of f of x equals big F of b minus big F of a. Okay, and this is only true. Here's the like precondition. This is only true if capital F prime of x is equal to f of x. Okay, so what this means is if we take an antiderivative of this function, that's how we evaluate the interval. Okay, so essentially what this says is, in words is we take the antiderivative of f, so this function inside the integral, and then we plug in the bounds and subtract. Okay, so that's fundamental theorem of calculus. This is going to stay with us for a long time, as you could imagine with that word fundamental in there, right? So let's see what this looks like. So find the integral of 4 in dx from 1 to 2, right? Okay, well, start by thinking of like what derivative, so let me write it out actually. So the derivative of what function gives 4? Okay, so that's a pretty easy one. So the derivative of only one type of function is a constant, 4x, right? So the derivative of 4x is 4. So that means that the integral of 4 is 4x. So the way we're going to write this, your notation when you're doing these should look like this. So I'm going to say equals 4x, and then I'm going to draw just a straight line up and down from 1 to 2. Okay, so this is a way of writing down the bounds once we've taken the integral. We're no longer going to rewrite that integral sign. Just like if you add two numbers, you don't write a plus again, right? So I've taken the antiderivative. We call this the antiderivative, by the way. And then I'm just going to plug in the bounds. So equals 4 times 2 minus 4 times 1. And notice the top one comes first in subtraction. That's important. And then that's just 8 minus 4 is 4. Okay, so that's your very first analytic integral. Okay, this makes sense too, because like if we picture this function, it would just be a little vertical line, right? At y equals 4, and then if our bounds from 1 to 2, we have a rectangle with width 1, height 4. Right, so 1 times 4 is 4. So this corresponds with area, and we can see that really easily when we have a constant function like that. So anytime you just have a plain old number in the integral, your antiderivative is going to look like this, and then your work is going to look similar to this. Let's try something a little more challenging. Okay, here's where your brain really has to turn on. So notice now we have a more complicated function. This is a linear function. And if you think back to like power rule, our antiderivative of this should then be a quadratic function. So like this first term is going to have an x squared in it, this term is going to have an x in it. So we're thinking what the derivative of what would give me negative 10x plus 1, right? Well, we know we're going to have an x squared because we subtracted 1 from 2 to get the 1 on my x. And then I multiplied some number by 2 to get negative 10. Well, that number would be negative 5, right? So you can check now. And this intuition takes some time to build. So I'm going to give you a fair number of practice problems here. So 2 times negative 5 would be negative 10, and then 2 minus 1. So that works, right? The general rule for this would be add 1 to the exponent and then divide by it. So I'll type that. So add 1 to the exponent and then divide by it. Okay, so that's how I got from negative 10x to negative 5x squared. And then plus 1, well, that's just like our last one. So the antiderivative of plus 1 is just plus 1x, right? Because the derivative of 1x is 1. I'm going to rewrite my bounds over here. And then I'm going to plug these in. And you got to be careful with your signs here. So negative 5 times 2 squared plus 1 times 2. And you're going to want to do parentheses, so we're subtracting this whole thing. And then negative 5 times 1 squared plus 1 times 1. Okay. Now, what do we get? So I get negative 14, and I'm just PEMDASing, right? Order of operations and simplifying. And you can just type it into your calculator straight across as well. Make sure you have these parentheses here and watch your negatives. Okay. So there is a power rule example. We'll do one more example just so you guys can start to see the pattern. Okay. So here we have an x squared. I'm still going to follow that same rule as I had before. Add 1 to the exponent and divide by it, right? So the antiderivative of my first term is going to be x to the third with a negative 3 coefficient, because 3 times negative 3 gives me that negative 9. Plus, and now we have an x here, so we're going to have an x squared antiderivative, and then an 8 in front, because 2 times 8 gives me that 16. Hopefully we're seeing the pattern here. It does take time to be able to do these quickly, but you should be able to follow my steps, I think. And then we're just going to evaluate the bounds. And this is a nice one because our second bound is just going to give us 0. So we'll get negative 3 times 2 to the third plus 8 times 2 squared. And then minus that second one, but that second one's going to be 0. Okay, and then my result for this, I'm going to, PEMDAS, still do my exponents first, multiply, and then add. My result is 8, and you can check that on your calculator. Okay, so make sure you check your understanding. Like, make sure you can explain how I got these antiderivatives from the given function. That is the most important step here. Take a second, make sure you have these examples captured in your notes because these are going to be the helpful 2 examples as you work through the practice problems. Make sure you go back and rewatch if you're confused. This is worth your time to make sure you understand really deeply because we're going to use this for a long time.